Hello, Hornets. Welcome. This evening, or today, or whenever you're watching this, we're going to be talking about differentiability. Now, up to this point, when we've been doing our difference quotient, remember that's what we've been working on? That's the limit as h approaches 0 for f of x plus h minus f of x all over h. Now, in this wonderful function that we have here, we've already identified that in order for this to happen and be called a derivative, we've had to have our result come out as a 0 over 0. Now, there are a couple of other criteria that we haven't really touched upon, but now is the time. And that's that when we plug in our 0, or our h equals 0, notice what we get. In the numerator, we get f of x minus f of x. And this will yield a 0. Okay, now that's obvious because when we do our h equals 0, we get 0 over 0. That's just part of what we've got. Well, what this tells me is that my function that I'm taking the derivative of is our f of x. And if we now use our notation that we've already started talking about, d dx, we're now saying that whatever we get is the limit that comes out from our difference quotient. Okay? Now, we've looked at a lot of functions. We've looked at those that are quadratic in nature. We've looked at those that are cubic in nature, quartic, but they've always had certain characteristics that we haven't yet talked about. And one of these characteristics is smooth. Now, look at what our function is. This is the limit as h approaches 0. Now, we can also call it the limit as delta x approaches 0 for our f of a plus delta x minus f of a all over delta x. We've even seen this as the limit as x approaches a for f of x minus f of a over x minus a. All of these were forms of our derivative. And all of them are limits as the slopes approach the same thing on both sides. Remember, this is what we were talking about in one of our videos, where we were looking at that falling object problem, and we were looking at the difference quotient itself. And we were looking at the two lines or slopes approaching each other from two different directions. Okay, no matter where it was on our graph, we were always looking at it as our delta x approaching 0. Now, there's one graph we haven't looked at. This is also a function, but look at what happens in this one. This is an absolute value, and we will call it the limit, the absolute value of x minus a plus b, and this will be our f of x. Now you'll notice our limit as h approaches 0 for our f of x plus h minus f of x, and we'll put in our a. Let's just make sure we have that all over h. This is going to give us a negative value, isn't it? Because we have a negative slope there. But look on the other side. The limit as h approaches 0 for f of, and now we're approaching left and right, we're breaking it up into the two one-sided limits, a plus h minus f of a all over h, now has a positive slope. We can see that because the graph is obviously positive in slope. Well, that means that at x equals a, the limit from the left doesn't equal the limit from the right, and therefore we do not have a derivative. This is called non-differentiable. Okay? Differentiability requires continuity, but it also requires a concept of smooth. Think about a roller coaster. If you're trying to build a roller coaster, the last thing you want to do is have a jagged edge. Imagine a roller coaster doing that. I would not want to go onto that roller coaster, would you? That would be terrible. This is a sharp edge where the slope from the left doesn't equal the slope from the right. And nothing we can do is going to change a positive slope to a negative slope in a single value. Imagine you're designing a railroad and there's a building that you have to go around. Are you going to make edges and corners? No. If you do, the momentum of the train is going to go directly off the tracks and it will not work. So you end up having to have a smooth curve. And we refer to this as smooth. All right? And every value now that we choose along our domain has a limit of the slopes, where the difference quotient is now going to work for the limit as h approaches 0. That's our goal. So keep in mind that anytime you have different slopes, which will now mean a different derivative, at a value of a, where a is less than b, let's call that b, and then we have a different derivative, and we'll call this c, where c is now greater than b. If these two are not equal, we have a problem. All right, thank you very much, Hornets. We'll talk about this further in the next video. Take care.